Now that we have our grain size distribution curve showing percentage passing from different opening size or grain diameter, we want to see what can we learn about our soil. So the first thing that we're going to go over is called median size, which is the diameter of the sieve opening through which 50% of soil sample passes. So we want to know 50% of our soil is smaller than what size? 50% of the soil by weight is finer than this size. So we are looking at percentage passing of 15%, 50%. And want to see like 50% of the soil that we have is finer than this specific size. This is also referred to as average particle size. So for median size, which we use D50, we start from here, start from 50% passing, draw a horizontal line until it intersects with our gradation curve. That's point 2. And then from there, we draw a line that goes to grain diameter axis. This point here is D50. So for example, for this soil sample, D50 here is 1, 2, and 3. So D50 is close to 2.4 millimeters, which again, it means that half of our soil particles, half of our sample, 50% of the soil is smaller than 2.4 millimeters, or the average particle size in this soil sample is 2.4 millimeters. The next one is called effective size, or D10, which is 10% of our particles are finer than this size. The diameter of the sieve opening through which 10% of the soil sample passes. This is important especially for granular soil when we have sand and gravel. It can be a good measure to estimate the hydraulic conductivity or permeability and drainage through soil. So, effective size, very important for granular soil. It can let us know how well the permeability is, and it's 10% of our particles are smaller than or finer than this size. So now you start from 10% passing, draw the line until you get to the gradation curve, and then from there you move downward to the horizontal axis, grain diameter axis. This point is our effective size, or D10. So in this example, D10 is approximately, here we have 0.1, 0.2, 0.3, and 0.4. So it's almost 0.35 millimeters. 10% of soil is finer than 0.35 millimeters. Then we also need D30 and D60. So for D30, we start from 30% passing to the gradation curve to the horizontal axis. So D30 in this example is close to 1 millimeters. which means that 30% of soil is finer than 1 millimeters. Then we also need the 60, so here we start with 60% passing, go to the gradation curve, and then downward movement until you get to the grain diameter axis. So we have 1, 2, 3. This is 1, 2, 3. So the 60 is close to 3 millimeters, which means that 60% of soil is finer than 3 millimeters. So now we can calculate a property of soil which is called coefficient of uniformity. How uniform our sample is. How do we calculate that? Cu, coefficient of uniformity, is D60 divided by D10. So in the previous example, we had 3 millimeters, what was D10? 0.35. Divided by 0.35 millimeters. That's our coefficient of uniformity. So in this example, it's equal to 8.57. What is coefficient of uniformity? Again, it indicates the degree to which the particles are of the same size. So if we have a soil sample where all the particles have the same size, then Cu will be close to 1. But if we have a sample where we have particles, same amount of particles with different size, then Cu will be greater than 1. So again, Cu will be 1 if particles are all of the same diameter. Cu for a real soil is greater than 1 because we usually have a combination of particles with different sizes. And increasing values represent an increasingly wide range of particle size. So a larger Cu means that we have a wider range of particle sizes. If all the particles are of the same size, then Cu will be close to 1. This is what we call a uniform sample, where the majority of particles are all of the same size. And that's why it's called coefficient of uniformity. Then we have coefficient of curvature. So it's talking about our curve. If it's like this, if it's like this, or if it's like this. And its coefficient of curvature is D30 to the power of 2 divided by D60 times D10. So we had 1 millimeter to the power of 2 divided by 3 times 0.35. Coefficient of curvature indicates the smoothness and shape of gradation curve. Again, if we have curve like this, or like this, or like this, very high or very low values indicate that curve is irregular. What we want is something like this. So, calculating CU and CC, we can determine if a sample is well graded or if it's poorly graded. These two lines are the statements you can use to determine if a gravel sample is well graded or if a sand sample is well graded or not. A well graded sample is a sample where we have a high CU. If you remember, CU close to 1 means that we have a uniform sample, which is not suitable for construction application. We want a sample where we have a wide range of particle sizes. So a CU higher than 4 for gravel and a CU higher than 6 for sand. Then we have and, so both of these statements, CU and CC, needs to be satisfied so that we can say our sand sample is well graded or not. CC, again, we don't want a very high value or a low value. We want something between 1, 2, 3. So here you see I have 0.95, which means that this sample is not well graded. So this is important. Here you can see examples of different types of gradation curve. Again, we want a CU higher than 4 or higher than 6 and a CC between 1, 2, 3. So this is a well-graded sample because we have particles from 3 inches to 0.001 millimeter or 100 millimeter to 0.001. Then we said that if CU is close to 1, then we have a uniform sample. So if you look at this gradation curve, the range of particles is between 1 millimeter to 0.1 millimeters. Very small range of particles. So we can actually try to calculate CU for this sample. Coefficient of uniformity is D60 divided by D10. D60, D10. D60 go here, and then from here we come down. D10 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. So D60 is 0.6 and D10 is 0.3, which gives us 2. And these are the requirements for sand and gravel. So CU, if we say that this is a sand sample because it's less than 4 inch, then CU requirement is not satisfied, and this is a poorly graded sample. And we refer to it as a uniformly graded sample. The third example that you see in this slide is this curve, which is not as smooth in this area. And this is because we are missing, so the amount of intermediate particle size is lower compared to coarse and fine particles. This one is referred to as gap graded sample, where we are missing some intermediate particles. The amount of intermediate particles are lower compared to coarse and fine particles. Now let's calculate Cu and Cc for the well-graded sample. So I'm gonna erase everything else. Well-graded sample is the green line. We want to find D60. That's D60, which is 9 millimeters. D30, .1, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. And D10, which is 0.02 millimeters. So Cu is D60 divided by D10. It's going to be D60, 9 millimeters divided by D10, which gives us and Cc is D30 divided by to the power of 2 divided by D60 times D10, which is 0.6 to the power of 2 divided by 9 times 0.02. Which will be 2. So now if we want to check, let's say that we have sand. Cu should be higher than 6 and Cc should be between 1, 2, 3. This is higher than 6 and this is between 1 and 3. So we can say, confirm that it's a well-graded sample. And you can try to do the whole thing again for uniformly graded sample. And determine if it's a well-graded sample or if it's a poorly graded sample.